Hello and welcome. In this video, we're going to work with a question that involves sigma notation, and it's an IEB exam question that comes from 2020 paper 1, question 11A, and the question reads: determine the smallest value of k for which this sum added with that other sum will be greater than 1 million. In other words, there is some k value that if I put there, it will make the whole sum bigger than 1 million. So I need to solve that. I need to solve for that k. There's probably a lot of different k values. There's actually a lot, not probably. There's actually a lot of values that we can put there that will ensure that this becomes greater than 1 million. That will ensure the total becomes bigger than 1 million. But we are obviously looking for the smallest one that does that. That's the whole point of this. We need the smallest value of k that will do that. Okay, so you can't just say, oh, allow k to be 800,000. Obviously, probably that will do it. You can't just say that. You have to solve for the actual smallest value of k. Okay, so before we do this question, I'm going to give you a chance. Please pause the video and try and do it yourself and see if you can get to the smallest value of k that will do this. Okay, so I'm going to now solve this and let's analyze this one more time. So we need to find the smallest value of k for which when we add this sum and we add it with that other sum, together the total will be bigger than 1 million. And it's important to recognize that k is an integer. They're saying k here is an integer because, as we know, z represent a set of integers. Okay, that's just something to be aware of. Okay, so inside the question, it is clear that you've got two different sums, and these sums can be done individually before you have to deal with the greater than 1 million part. You can deal with that later. For now, I think we just need to figure out what each sum is actually if we do it. So just starting maybe with this one that is sum to infinity, we're going to need the first three terms, and that is just substituting from I equals 1 there. So we go k over 2, substitute the 1 because I starts from 1, and we got k over 2. Now we substitute 2 now, and we got k over 2. Now I is 3. Obviously, I can change this and make this k over 4 and make that k over 8, but I'm just going to leave it as is for now. And actually, yeah, I'm just going to leave that as is because I don't need to find it. So a then in this case becomes k over 2, and r, if you think about it, because you're just going to take this and divide it by the previous one, you would realize in order for you to move from here to there, you must have multiplied by 1 over 2. So r is actually just 1 over 2 in that. And you can show that by just taking this and divide it by the previous one if you'd like to do that. So now that we have that, this means now we can find the sum for this sum to infinity that's happening there. So sum to infinity will now become, as we know, it is a over 1 minus r. So it is a, which is k over 2 over 1 minus 1 half. Let me move my equal sign there. So 1 minus 1 half is obviously just 1 half. So this is a situation where you've got k over 2 divided by 1 over 2, and it's better to just change the division to multiplication and flip the 1 over 2 to be 2 over 1. allowing us to have k. So therefore we know S infinity is just k. So if you sum everything here to infinity, it's just k in that. So this sum is just equal to k really. In the end, that's what we find out. Now let's do the other one, the purple one. So that's not sum to infinity. That's summing from I equals 1 to I equals 10. So that's terms that we're summing there. And we're going to need the first three terms as well there. So in order for us to know what A and R are going to be. So the first three terms are going to be 2, 2, bracket, the first I is 1, and next 2, 2 brackets, the second I is 2, and we got 2 to the power 2 bracket 3. Now we got the first three terms, and if you want to find the exact values, that this is obviously going to be um, 4, and that's going to be 16, and that's going to be 64. You can write those values if you'd like to, but I'm just not going to do that. I'm going to leave it like that. I think it's sufficient to be able to know what A and R is going to be. So A is going to be this, which really is just 4. Okay, and R is, if we recognize this is, if we just take this and divide by this, we will find 2 to the power 2 as our answer. And you can do it as well by just knowing that this is obviously 16, and that's obviously 4. So if you take 16 and divide it by 4, we know the answer is 4. So R is also 4. And we're not doing S infinity for this here, because that doesn't sum to infinity. In fact, it wouldn't even work, because it sum to infinity requires the R to be between -1 and 1, and that R is way bigger than 1. So we need to find the actual sum to turn terms, because there are turn terms in that sigma there. Um, A is 4. I'm just using the formula here. And then it's got R to the power n, but R is 4 to the power n is 10 minus 1 over 4 minus 1. So that's what you do using the formula A bracket R to the power n minus 1 divided by R minus 1. So that's sort of what I'm using there. And if you calculate this using your calculator, you should get that this is 1,398,100. So that's what, and this is just the sum for that. This is just the total once you've done that sigma there. And remember what this one was. This was just k. We've done that one as well, and we know this one is k. So we've got these two, and we need to now put them together and understand that if we put them together, the k, I guess I can use a different color now just to finish this up. So if I take the k from the sum to infinity, and I take the 1,398,100, and that's supposed to be greater than 1 million. I wrote that million very weirdly. Typically, you want 3 zeros together and the other 3 zeros together. That's just easier to read. Okay, so you're looking for this, and you want k plus this number to be greater than that. And this is a simple thing to solve. I mean, really all you need is just to move that over to that side. And then you'd find that k must be greater than negative 398,100. So k has to be greater than that. And the first integer, basically the first integer which is greater than this, would suffice, would be the solution. So therefore k, sorry about this, therefore k is equal to The first integer, which is bigger than that one, is negative 398 and 99. So negative 398,099. That's the first integer which is bigger than this one. So that is the smallest. This then would be the smallest k value that would ensure the condition that's given. So as a reflection to this question is one of the things you need to know is once you have a sigma like this, you can always evaluate that thing and know what it is. And in fact, it is helpful to do that because when it's like this, it's just so complicated. It even looks complicated. But if you could actually evaluate the sum, then it's a lot more simpler. Look at how simple it becomes. That first one, there's a green one and the purple one, right? So let's look at it. There's a green one and the purple one, the ones I highlighted with green and purple. So once you've done it, you realize the green one is just k and the purple one is just 1,398,100. And then it's a lot more simpler to think about the question in itself just by doing this work first. Find out what the sigma is, and you can solve that. That's a pretty simple question after this is done. So this is a 6 marks question, and yeah, I think this is a good place to stop. We've done everything that is required. We found the smallest k value that would guarantee greater than 1 million. Thank you for watching, and I'll see you in the next one.